Welcome back, students. Video number 27 of the same chapter, that is chapter number 4. We are looking for Amperes Circuit Law. In previous video, we have seen equation of magnetic field for a solenoid. Now, in this video, we will see equation of magnetic field for a toroid. What do you mean by toroid? Let us see. Toroid, or it is known as toroidal ring also, as well as Dug-knot tube. So this type of Dug-knot tubes we are using in swimming pool. That circular tube for small kids, when they are in swimming pool, they are using that Dug-knot tube. Okay. Now let us see what is toroid. That means how it can be prepared. A long solenoid. This long solenoid is bent in the form of circle. So long solenoid, you have to bend in the shape of circle. Okay, and the ends of long solenoids are connected with each other. Got it? Let us say, suppose this is a long solenoid, then you have to bend this long solenoid in the shape of a circle. Okay, then it becomes like this. So this is the long solenoid, you have to bend in the form of circle, so it will be like this. Okay, so our long solenoid, now it becomes a toroidal ring. So let us see, toroidal ring is like this. Okay, so it is a solenoid which is bent to form a circle. Simple. And over this we have to wind a wire which is closely wound. Got it? So this is the simple mechanism of a toroid. Got it? So toroid is nothing but it is a long solenoid which is bent in the form of a tube. Electric current is going inside, that is I, and here coming out. Okay, and we know that inside the solenoid, that means here, there is uniform magnetic field. Got it? So this is the construction of toroidal ring. Here dotted line indicates the magnetic field which is uniform, which is constant inside the toroidal ring. Okay, let us take 2 points here, point P and point Q. See, we are combining two figures of our textbook which is given on page number 152. Instead of that two figure, we are taking only one. Got it? So, this is the center of that toroidal ring O. It is a point P having radius, suppose small r1. This is the point Q having radius, suppose r2. Got it? So you can say that point P and point Q, they are outside the toroidal ring. That is why closed integration of BTL is equal to mu 0 I. It is our Amperes law, but you can say that at point P and at point Q they are outside, therefore magnetic field is 0. But there is one more aspect. At point P and at point Q electric current passing is 0. So here you can put like this, mu 0, electric current at point P and Q is 0. So it is also becomes 0. Got it? Means it is a simple thing like a solenoid. In a solenoid, outside magnetic field is 0, inside magnetic field is constant. The same way, point P and Q, it is at a distance r1 and r2 from origin respectively. As you know, these 2 points are outside the toroidal ring, therefore magnetic field is 0. Simple. But here one more thing it is given in our textbook. So through the point P and Q, electric current passing is 0. Therefore magnetic field is also 0. Where? At point P and at point Q. Okay? Now let us see. Consider this radius. Now it is the point which is inside the toroidal ring. Consider this radius R. Consider this point. Which point? Suppose it is M. Got it? So let us see. Consider point M which is inside the toroid and which is at a radius small r. Got it? So according to that law, which law? Amperes Circuit Law, closed integration of B dot dl is equal to mu 0 I. This is for a 1 ton is equal to n multiplied by mu 0 I. So this is the equation for n number of turns. Got it? So now when we are going inside the toroid, so inside the toroid at point M, current element, that is IDL, is parallel to magnetic field B. Same situation was there in solenoid also, and because of this reason theta value 0, and we know that cos 0 value 1. So our equation becomes what? Close integration, that is B dl cos theta is equal to mu 0 capital Ni. Okay, cos theta is nothing but cos 0 and cos 0 value 1. So our equation becomes close integration b dot dl is equal to mu 0 capital Ni. Here b, what is b? B is nothing but it is uniform magnetic field inside, and it is nothing but constant. So take it out. So we are getting b close integration dl is equal to mu 0 capital Ni. Have a look once again. This is a toroid. How to make toroid? It is very easy. A long solenoid is bent in the shape of circle, and the ends of that solenoid is connected with each other. So it forms a toroid, or you can say that toroidal ring, or in few reference book it is also known as Dug knot tube. Okay, on this toroidal ring there is a winding of wire which carries electric current in, electric current out. Got it? Now for this toroidal ring, consider 2 points P and Q at a distance R1 and R2 with respect to origin O. But this 2 point is outside the toroidal ring, or at these 2 points electric current is 0, therefore magnetic field is 0. Means outside magnetic field is 0 like a solenoid. Now we have to consider a point M which is inside the toroidal ring. It is at a radius small r. So for this, according to the Amperes law, close integration b dot dl is equal to mu 0 I. It is for a one turn, but this toroidal ring consists of n number of turns, so it is capital N mu 0 I. So at this point, current element and magnetic field lines are parallel to each other. Theta is equal to 0, cos 0 is equal to 1. So our equation becomes cos 0 value 1. B is constant. Take it out in close integration of dl. What is close integration of dl? Let us see. Once again we are writing the same equation. That is close integration of dl is equal to mu 0 capital N I. Here close integration of dl is nothing but circumference of a ring, and it is given by 2 pi small r. Got it? What is r? R is nothing but radius of the ring. Okay, so instead of this integration dl, we have to take 2 pi r. So our equation becomes b multiplied by 2 pi r is equal to mu 0 capital Ni. Make a subject b. So b is equal to mu 0 as it is, Ni as it is, upon 2 pi r. What is this? Same as we have done in solenoid. So it is nothing but b is equal to mu 0 small Ni. Again What is small n? Is nothing but n, number of turns, 2 pi r. It is circumference of a ring, so it is nothing but number of turns per unit. 2 pi r means length, and it is nothing but number density. Got it? So this is the final equation for a toroid. Oh sir, wait, it is the same as solenoid. Yes, why not? It is the same as solenoid, but there is a difference. Let us see which is the difference. So these are the points that you have to remember. What to remember? Let us see. Let us take that equation, that is B is equal to mu 0 small n I. Right? So this is the standard equation. Here, if we take this n, that is n is equal to n by L, that is number of turns per unit length, that is h. So our equation becomes B is equal to mu 0 capital Ni upon h, and this is the equation for a solenoid. Got it? But for a same equation, if we are taking n is equal to number of turns upon circumference of a ring, that is 2 pi r. Okay, then we are getting the equation, that is B is equal to mu 0 capital Ni upon 2 pi r. So this is the equation for a toroid. Got it? Simple thing is there. This is the small analysis between solenoid and toroid. Just there is a difference of small n. What is small n? That is number density. Okay? Only this much is the difference between equation of solenoid as well as toroid. Equation is same. See, B is equal to mu 0 Ni, but the value of n is different. Okay? Have a look. Clear? For solenoid and toroid, one thing is also common. That means magnetic field is directly proportional to electric current passing through the solenoid or toroid. Got it? Okay, from this equation, one more thing is there. H. What is H? That is the length. Length increases, B decreases. So for a solenoid, as length increases, magnetic field decreases. Same thing for a toroid. C. What is R? Radius. As radius increases, B. magnetic field decreases, and vice versa. What it indicates? It indicates that if the length of a loop is small, then magnetic field is more, or as we wrote here, if the length of a Amperes loop increases, magnetic field decreases. As radius of a ring increases, magnetic field decreases. Simple. So these are the few questions for MCQs. Have a look. Okay, it is also a 2-mark question, and question can be asked like that. Obtain the equation of magnetic field for a toroid. Have a look. Thank you.